This is Climate Change with a Touch of Geology, presented by Ethan Hoy. So, I wanted to cover for this documentary a little bit about climate change and how it relates to geology and what we know about it as a society. So, climate change as a whole is the gradual shift in Earth's climate because of greenhouse gases being released in the atmosphere. What that means is greenhouse gases lead to a change in our climate, typically hotter as we increase the amount that are located in our atmosphere. How do greenhouse gases work? Greenhouse gases trap incoming solar radiation after the heat bounces off the surface of the Earth. Humans produce greenhouse gases, and some examples are CO2, CH4, which is methane, N2O, which is nitrous oxide, etc. So if you look to the picture to the right, we can see that incoming solar radiation is being brought into Earth by the sun, and it goes through our atmosphere and it goes towards the surface of the Earth. If you follow my cursor, you can see that it bounces off the surface and escapes out into space. But greenhouse gases greatly impact this cycle. Instead of that solar radiation bouncing off and going into space, the greenhouse gases trap it again once it tries to go out of the atmosphere and into space, so they bounce back towards the Earth. That means that more heat is trapped in Earth's atmosphere, which changes our climate greatly and makes it warmer. Down below, I have a picture of the different types of greenhouse gases. So we have CO2, methane, nitrous oxide, HFCs, PFCs, and then SF6. So these are just some of the greenhouse gases that are common. Water vapor is also another one that traps a lot of heat, but we don't talk about that a lot because the amount of water vapor remains pretty stable in the atmosphere overall. So I wanted to relate this to geology as a geology major. So I wanted to cover that we should actually be in an ice age right now or heading in that direction. Climate naturally oscillates between glacial periods and interglacial periods. According to previous data, we should be heading towards a glacial period, but anthropogenic forcing has changed this. So if you look to the little diagram on the right, you can see that climate was actually starting to drop again towards a glacial period instead of peaking up towards a interglacial period or a hot time where we don't have a lot of glaciers or any present. This is significant because it tells us that humans' impacts or anthropogenic impacts have been so great that we've actually completely altered the the way that ice is present on the planet. And we are beginning to put enough greenhouse gases in the atmosphere to heat up the entire planet and change the way that our glacial and interglacial cycles oscillate. So I wanted to relate this to geology specifically because there is something called the Blagg hypothesis. What the Blagg hypothesis suggests is that changes in seafloor spreading rates influence atmospheric CO2. Basically, this hypothesis believes that whenever the ocean floor starts spreading, and they spread at different rates depending on how many faults are present, along with the movement of plates and tectonics, the Blagg hypothesis suggests that that influences how much CO2 is naturally released out of our planet. Also, something that's notable is something called methates or methane hydrates around the location of these areas where C4 spreading is occurring in subduction, because when these hydrates are broken similar to glass, they release a significant amount of methane, which is also a very potent greenhouse gas, much more than CO2. What moderates greenhouse gases? So another thing that I really want to tie this into with geology is that chemical weathering is the primary force behind moderating CO2 in the atmosphere and other greenhouse gases. Chemical weathering it affects how much CO2 is in the atmosphere because whenever it occurs, it takes CO2 out of the atmosphere and sequesters it under the ground. Chemical weathering's impact is dependent on how much fresh rock is exposed or newly exposed rock. This tends to occur during near mountainous regions where we have an excess of fresh rock exposed because when rock breaks up, it has more surface area exposed, even if it's smaller fragments in total. This means that with more surface area exposed, more chemical weathering can occur and sequester more CO2. So typically, when we have a more mountainous or more large mountainous regions on the planet, we see that occurrence of an excess of chemical weathering, which helps greatly lower the amount of CO2 in the atmosphere, kind of working as an opposite to the Blagg hypothesis. The impacts of climate change are pretty well known, but just some for reference are impacting our our quality. It can cause extreme heat, drought. We can destroy our environment because it harms what lives in the environment. It causes severe weather. We can have food scarcity issues, water quality, wildfires, smoke, etc. And lastly, I want to talk about why we need to do something now and not wait. Climate change is based on feedback cycles, positive and negative feedback cycles. So, with positive feedback cycles, we see that as the planet begins to get warmer, it's going to only accelerate the speed at which that occurs. So that's significant because it tells us that we're looking at exponential growth. We're not looking at linear. And that also tells us that it's even harder to stop climate change once it starts occurring versus negative feedback where whenever something changes, we can change it and slow it down. Um, we don't have that. We have positive feedback, meaning that the process is only accelerated when it occurs. So this is very significant.